Hello and welcome to WinXAS Tutorials. This is the first video in a series of tutorials where I want to talk about using the WinXAS software to analyze experimental data from X-ray absorption spectroscopy measurements. Except for this first video, tutorials will consist of two parts. The first part will contain a brief introduction to the analysis procedure covered in the tutorial. The second part will contain a hands-on session where I will be using the software to analyze selected experimental XAS spectra. The WinXAS software and the experimental data can be obtained from the WinXAS website. The data reduction and data analysis procedures I will be talking about in the tutorials are shown here. Data reduction includes pre-treatment of experimental data, energy calibration and background correction, followed by atomic absorption correction and Fourier transformation. Data analysis refers to analyzing the XANES and the EXAFS region of an X-ray absorption spectrum. For the XANES region, this may be profile fitting, for instance, to determine the average oxidation state, and principal component analysis to determine the phase composition. For the XAFS region, this includes calculation of theoretical XAFS function using both experimental and theoretical phases and amplitudes, as well as XAFS refinement to obtain structural parameters. I will talk about the significance of those parameters and how to calculate that. And eventually I will be showing how to use all these procedures in the analysis of larger sets of spectra like those obtained from time-resolved experiments. For clarification, the results of the data reduction procedures mentioned are depicted here. Data reduction starts with the raw XAS spectrum showing absorption as a function of photon energy in keV. After energy calibration and background correction, the atomic absorption is determined and used to obtain the XAFS chi of k function. Eventually, this chi of k function can be Fourier transformed, resulting in a pseudo-radial distribution function as shown here. XAFS data analysis now uses the previously obtained chi of k or Fourier transformed chi of k function to obtain structural parameters. Therefore, a theoretical XAFS function based on a suitable model structure is being calculated and compared to the experimental spectrum. Given a good agreement between theoretical and experimental XAFS function, structural parameters such as nearest neighbor distances, coordination numbers of various coordination shells around the absorbing atoms, and disorder parameters can be obtained. Let's finish this first tutorial by briefly explaining what I will not be talking about in the following tutorials. In general, I will not cover the theoretical background of X-ray absorption spectroscopy. This includes, for instance, what parameters of the electronic or geometric structure of the absorbing atoms can be obtained from analyzing the XANES or the XAFS region of an experimental XAS spectrum. Also, I assume that you know the meaning of XANES and EXAFS and that you are familiar with the fundamentals of photoionization, scattering and backscattering of the photoelectron and Fermi's golden rule. you should already know the basic data reduction and data analysis steps necessary to extract the structural parameters that you are most interested in. Eventually, I assume that from the following WinXAS tutorials, you merely want to learn how to use the WinXAS software to perform the analysis of your own experimental XAS spectra. Finally, I will not talk about instrumentation for X-ray absorption measurements. This includes sample preparation, appropriate thickness and absorption, sample holders, and the design of the various spectrometers available to perform XAS measurements under a variety of conditions or time scales. Again, I assume that you have a decent set of experimental spectra that you want to analyze in a convenient and time-efficient, but also transparent manner. And this is exactly what I want to talk about in the following tutorials. Well, that's it for this tutorial, and I hope to see you in the next one.